Well, hey everybody. We're going to talk about Newton's laws today and the three different laws, things like that. And before we jump into that discussion, I'm a really big history of science buff, so I really enjoy reading about the history of science. And so there's a little video sort of about the history of Newton's laws that I'd like you to watch. So let's jump to that real quick. Let me mute my microphone so we can all listen to the video together. Okay, so now they watched the Newton video. This is an interesting bit of trivia about me. This is not in the main slides for that you guys are looking at on Carmen, but this is your bonus for watching the video here, which is that. So here's Sir Isaac Newton up here. Here I am down here. Maybe you can already figure out where this is heading, but so there's Newton. You know, here's me over here. So Newton, why is Newton's name? All right, so Newton looked like this, and he was at Cambridge in England. Now, James Clerk Maxwell, Newton was not Maxwell's advisor. They didn't actually overlap. Maxwell came much later, but they were both at Cambridge, and so they're both breathing the same intellectual air and drinking the same intellectual water, you could say. My advisor is David Weinberg, who's the current chair of the astronomy department at Ohio State. He's my PhD advisor. Now, Maxwell was not actually Arthur Eddington's PhD advisor, but they were both at Cambridge, and again, they may have overlapped, I can't remember. But again, drinking the same air, breathing the same air, drinking the same intellectual water. David Weinberg's advisor was Jim Gunn. I ran into him at a conference once, and he asked me who I was working with. I said, David Weinberg, and he says, oh, well, you're like my academic grandson. I was like, yeah, it was a nice moment. Jim Gunn was awarded the Presidential Medal of Freedom for his work, or the Presidential Medal of Science for his work on the Sloan Digital Sky Survey. His advisor was this guy who is not in Star Wars. So before you can ask that question, I know he worked on stars. I don't know too much about him, but his advisor was Chandrasekhar, who's super famous, and there's like a satellite named after him. He did all sorts of impressive stuff. And then Chandrasekhar's advisor really was Sir Arthur Eddington. So my academic ancestry goes seemingly up to here. Arthur Eddington's super famous in the field of astronomy. Anyway, so later we'll talk about, especially in Physics 1251, we'll talk about Maxwell. There's an astronomy course I like to teach. I talk about Eddington, physics of stars, stuff like that. So in any case, so this is my academic ancestry, and now here's you. So do your intellectual ancestors proud this semester and give it everything you got, all right? Great. So let's talk about Newton's laws of motion. This is Newton's first law, which I would explain it as an object at rest or moving in a straight line at constant speed if there's no forces acting on it, right? So if you throw a baseball into space, if there's no gravity acting on it, it'll just move into a straight line. So what I want to say is that people have heard these sentences before, but here's mathematically what it means is that the distance is the velocity times the time, and so if you have some velocity, as time goes on, your distance becomes larger and larger and larger. So so this equation encapsulates this idea of moving in a straight line at constant speed. And if an object is at rest, velocity is 0, that means the distance is 0 for all time t. So an object will, if an object is at rest, it will remain at rest for all time t. So that these sentences sort of connect to that, connect to this mathematics here. I think I just said this already. Newton's second law is that has to do with forces and acceleration. And so, first of all, acceleration is a change in velocity with change in time. We talked about that last time. Not necessarily change in speed, but change in velocity. And a force can cause an acceleration. So the next equation is So this is a Jedi applying the Force, right? So the Jedi, the more force that the Jedi applies, the more that the droid accelerates. And so the more force, the more acceleration, but the more mass, the less acceleration. So for example, I'll show you a video of that in just a second. So because the more mass, the less acceleration, then in this way you could say the mass resists acceleration, so to speak. So here's an example. So here's the rocket car. We're actually going to try to analyze this video. And so, again, this is a dude with a fire extinguisher. And this is a constant force, more or less. And it's on rollers, and so he accelerates. In the video analysis, we can try to show that the velocity is steadily increasing. You can kind of see it from the video that it starts out slow and it goes faster and faster and faster. It's a little bit subtle. In this video, he's not sitting on it, and you can see how it goes fast, even faster, right? The important thing is that it's accelerating faster at a faster rate. And so that gets back to this equation, right? So it's the same force in both times because it's the same fire extinguisher. But in the second case, the mass is much less, so the acceleration is much more. That's the basic idea of it. Okay. All right, Newton's third law of motion. Some people call this action-reaction. For every action, there's an equal and opposite reaction. Here's a silly example of shooting a machine gun from a skateboard. You get shoved in the opposite direction, right? Not that I recommend that, but theoretically, that's what you would do. This is a silly video that I found online. So this kid is going to jump off the boat. And the basic idea is that for this kid to move forward, this kid applies a force on the boat in the opposite direction that he wants to jump. And so the boat, applies a force on the kid and that's how the kid ultimately moves forward, right? So somehow this kid moves forward, clearly, right? Because he's pushing on the boat and the boat pushes back on him. And so the boat goes backwards and he goes forward. And again, it's all from the fact that the forces are equal and opposite. Now, there's an exception for Jedi. So when Jedi, force push things, the Jedi don't get pushed backwards. So I don't know whether the Jedi are violating the laws of physics or whether the Jedi have near infinite mass. You guys can debate and discuss that as much as you want. But that's the basic idea. Okay, so in the fire extinguisher video, we saw how the mass affects the acceleration and the motion. Mass is sometimes called inertia, and you can think of it as like the resistance to motion, resistance to changes in motion, or resistance to acceleration. Obviously the mass is the amount of stuff. Now, what's interesting is that there's a difference between your weight and your mass. So your weight, depending on which planet you're on or whether you're in space, that has a big effect on the weight, because the weight is the force of gravity acting on your mass. And so your weight on the Earth is whatever it is, but if you go to the moon, the gravity on the moon is 1/6 of what it is on the Earth, and so your weight is 1/6 of what it is on the Earth, assuming that your mass is the same. And so, in principle, your weight, if you're in orbit around the Earth, or if you're out in the middle of space and there's no forces of gravity on you, then you would be weightless. But your mass is still there, so you still have your mass. The mass is not necessarily changing. The unit of mass in this course is kilograms, as you may know. Now, in the next slide, not this slide, but the next one, I'm going to talk about the units of acceleration, velocity, and force. Before I do, I have to explain what this symbol is. So this is delta. It always means the final minus the initial. So the final x position minus the initial x position, for example. When I was in undergrad, I would always get confused whether it was the initial minus the final. But nope, it's always the final minus the initial, whether it's the x position, whether it's the velocity, whether it's the time, so the final time minus the initial time. So you can think of delta as the change in. It's not a coincidence. Delta Airlines is sort of like alluding to this idea that it's changing your position, delta. So it's kind of clever that way. Anyway, so delta, change in. All right, so the SI, let's talk about the units. So velocity is the change in distance over time, and so distance has meter units. Time is second units in the SI system. Acceleration is the change in velocity over change in time. And so the velocity is meters per second units, and then time is another factor of seconds, so that's going to be meters per second squared. And then the force is the mass times the acceleration, and so it's basically this times kilograms. And what we're going to do is we're going to define this to be we're going to find this to be a newton. So this is, and this fancy equal sign just means defined to be, so you can press your friends. I could have just done equals and that would have been fine, but anyway, so this is the unit of force, and we name it in honor of Newton there. Now forces are vectors, which is why we had the vector lecture the last time, and that means that forces can add together. Vectors are somewhat helpful in 1250, and there's a homework on it. The Essential Skills is going to have a bunch of vectors things. In my personal opinion, this is mostly to prep you for the way that vectors come into play into Physics 1251. But vectors are going to be super, super, super important for engineering statics, where you try to figure out like all the stress and strain and stuff. There's going to be vectors all over that course. So this is not just some physics thing or some math thing. It's for engineering applications. It's going to be very important too. There's a reading quiz question that I really like, that asking that if you applied the same force here and here, the components of that force, or if instead you just apply this force at some angle, do you get the same reading on the scale? Again, the stipulation is that this force would have to be the x component of this thing, and this force would have to be, or this force would have to be the y component, this force would have to be the x component. Do you get the same reading on the scale, right? So you have this spring scale here. Yes, you would. So again, the components have a real meaning here, and that's going to be helpful. I think I probably talked about this in the vectors lecture, but it's a good thing to think about. Now, the worksheet for today, this is a movie I really like, the Grand Budapest Hotel. I'm a bit of a Wes Anderson fan. There's not a whole lot of gondolas in Ohio. I guess if you work in Mad River Mountain, maybe you've been on the ski lifts or whatever. But we're gonna think about how much tension is in the wires to hold this thing up, and the tension on this side may or may not be the same as the tension on the other side. Just for the heck of it, so normally in a classroom, I would set up a string in the classroom, and I would tie, a standard kilogram to it. I'm not in the classroom this semester, so I took a stringy thing and I tied a butter knife to it. And the reason I'm doing this, and the reason I do it in the classroom, is because you can kind of see that this angle here is not the same as that angle. It's like a different angle here because it's holding the weight of the thing. And if I could show you in person, I can tell you that when you pluck these things, it feels a little bit different in terms of the tension. So anyway, I did this to kind of demonstrate. The question here is the tension in the wire the same on both sections connected to the gondola or the butter knife or whatever? So are these tensions the same, or are they different? What do you think? In a real classroom, I'd ask you to talk to your neighbor at your group, but obviously you're not in a real classroom. But is this the same tension from this side to the other? Well, I'll tell you. The answer is no, and in fact, if you pluck the little string here, you'll notice that this one is a little bit tighter than that one. Now, exactly why that is something that the worksheet's gonna work out. And the basic idea is that we give you some angles here, and I hope you believe us now that these angles are not the same, right? Because you can see that. be fun if you guys could try to do this yourself and try to measure the angles just from the photo. Like, how would you do that? Because, I imagine there's something like that might come up with an engineering context. So again, the worksheet for today is to try to calculate what this tension is and what this tension is, based on the idea that you have this 500 kilogram gondola. So that's the worksheet today, and we'll help you with that. And till next time.